Hey there, everybody. Welcome back. In this section, we're looking at LaGrange multipliers. We just got done looking or learning about the absolute maximum and minimum and finding the extrema for surfaces, 2D surfaces and stuff like that. And we're expanding upon that. So let's say we have a continuous function f of xy. It's in some region in 2 space R2, and it has a smooth curve C. Let's say that C is just some function G where it equals 0. And G is a function of X, Y also. We're going to assume that F has a point P naught where P naught is a local extremum of X, Y. So it's either a maxima or a minima. And so P naught is an extrema of F on C, and thus the gradient F is orthogonal to the line tangent to C. We're going to see that in a second. Just as a reminder, though, if the gradient or the local extrema occurs where the gradient is 0, call doing that. And we'll see that it shows that it's orthogonal to C. Let's assume for our smooth curve C that the gradient of G at P naught does not equal 0. Then there's got to be some scalar multiplier lambda such that the gradient of F equals lambda times the scalar or the gradient of G, both evaluated at P naught. So we have a function that has an extremum at P naught. We have a smooth level curve when we have function equal to 0. It's a level curve at that same point. The gradient, we're going to show these two are equal. Let's go to the proof. We start with C, and we're going to parameterize it with arc length S. So R of S equals X is a function of S, Y is a function of S. And that means P naught will be functions of S as well at a particular value of S. The rate of change of F as we vary S along the curve is df ds equals df dx times dx ds plus df dy times dy ds. If you check it out, this is the dot product. We've got df dx. I'll write it above it. df dx, df dy. Dotted with dx ds, dy ds. So this one is the gradient of F, and this is the derivative of R as a function of S. Okay. So we've got the gradient of F dotted with R prime of S. That is with the parameterization. That's the rate of change of F. We say at P naught, we had assumed that there's an extremum, which means that rate of change is 0 right there. We've hit either kind of like a high, like a mountain or a valley. And so that equals 0 there. Now, R prime of S is tangent to the curve C. So the gradient of F dotted with it kind of implies that F is orthogonal to C. Because we've got the curve, R prime of S is there. And if we've got the gradient of F and if this is the tangent, R prime of S, and this is our gradient of F, the dot product equaling 0 implies that F is orthogonal, or the gradient of F is orthogonal to C at P. Also note that we've got G being a level curve. And when we do gradients of level curves, the gradient function of a level curve is also always orthogonal to C. In fact, remember when we did that, the gradient along a level curve always pointed in the direction of steepest ascent. So, lambda, or the gradient of F and the gradient of G are both orthogonal to C at that point. which means they must be parallel. And so one's got to be a multiple of the other. We don't know how much of a multiple. So we use its lambda as the scalar. And even though this proof was in 2D, the idea scales up to 3D. And so we're introducing lambda as a new variable. We got to find values of lambda and at x, y, z, which is our p naught, that satisfy the gradient of f equals lambda times the gradient of g. And then we can evaluate to find the max and min. So we can find the extreme. We know it's an extrema, so we know it's a max or min there. And we'll be able to figure out where and what it is. Now, one way of looking at this is we've got some big function, and f of x, y may go over all of it. It may be everywhere. And g of x, y is just some very particular curve on it. That's our g of x, y. It's a level curve in our f of x, y that has a bunch of different options. So what we're doing is we are putting a constraint. G of x, y acts as a constraint on what we're doing. Acts as a constraint. So we will call f our objective function, and g of x, y will be the constraining function. It limits what curve we're looking at, what's going on, okay? Now, f doesn't need to be level curves like this. We just know that it has, like, if there is we know that, let's see, the gradient of g is always pointing in. Let's go to this one. I'll do it right there. It's pointing to a higher ground. Let's say that higher ground is up here. There's a peak inside. And f could be doing lots of things, but it's an extremum right there as well for f. G of x, y may be a level curve there. F may be an entirely different picture. It might have a hill right there, its own hill. But either way, at P naught, so my F is in blue, my G is in green, we're like constraining where we are on F by this level curve G. So it's where these two intersect. So it makes a very particular spot on F. So it acts as a constraint function. We'll see more in the next video. That was a little wordy. I think examples kind of make this shine a little bit better. Let's do it. Peace.